So far we had seen about the subspace characterization using Gramians. So whatever the result we have obtained in this theorem, we can directly apply to determine whether the system is observable or not. So this results not only provides a first method to provide to determine whether a system is observable constructible, but it also provides the characterization of the subspaces which we would use in the later concepts. So this Gramian has a direct implication. So let's see. So it says that the unobservable subspace from T0 to T1 is equivalent to the kernel of this square matrix WO of dimension n. Now, if we go back to the definition of the observability, it says the unobservable subspace should contain zero vector, right? Then the system is observable. Now, if it contains the zero vector, then the kernel of that matrix should be zero. It should not contain any vector, and this is only possible if the matrix itself is non-singular, because in the previous theorem we had seen that the Gramian matrix is a positive semi-definite. Okay, so based on this we have the next result, that suppose we are given two times t1 greater than t0 greater than equal to 0, the system continuous time LTV is observable if and only if the rank of the observability Gramian is equal to n. Okay, similarly it's for the constructible system. In satisfying this rank condition means that the square matrix are non-singular. Okay. Now we can again use this Gramian to actually reconstruct the state. So consider again this LTV system given by this pair A, B, C, D. We have seen that the system state x0 at time t0 is related to its input and output on the interval, this one. And this we have obtained from the variation of constants formula we had seen earlier. So y tilde is nothing but a subtraction of the terms containing the output signal and the function containing the input signal. Okay, so basically we want to construct this x0, and we had seen earlier difficulties that if my C is a non-singular matrix or is not invertible, then I cannot compute this x0. But using the Gramians, we would see that how we could do the reconstruction of the x0. Okay, so we'll pre-multiply by this vector where phi is the state transition matrix and C is the output matrix. And so let's write it here once again so that there is no confusion. We have y tilde Okay, this is the equation we had obtained. Now if I pre-multiply this above equation by phi transpose and C transpose and then integrate it, I would obtain on the left hand side phi transpose C transpose y tilde dt, and on the right hand side I would obtain phi transpose C transpose multiplied by C phi and x0, and here x0 is a constant, so I can take it inside the integral or outside the integral, right? Now keeping the left hand side as it is, and notice this whole term, this is nothing but your observability Gramian. So I can replace this on the right hand side as observability Gramian multiplied by x0. Okay, now taking the property of the observability which says that the observability Gramian is invertible or it is full rank, then it is possible to take its inverse, which is a square matrix, to perfectly reconstruct this x0 using this formula. Okay, similar construction can be carried out to reconstruct x of t1 from past inputs and outputs for reconstructible systems, right? So we have the immediate result that suppose we are again given two times t1 t0 and an input output pair uy for all time t belonging to t0 and t1. So when the system CLTV is observable, we can compute x of t naught using this formula, where y tilde is given by this one, and when the system CLTV is constructible, again we can compute this x of t, okay, using this uh, constructible Gramian. Now generalize whatever the results we had seen, it's in the continuous time domain. We can generalize all those results in the discrete time domain also. So consider this A, B, C, D, again the time varying matrices where T is now an integer. So by using the variation of constants formula, we had seen in the first week the solution of the discrete time LTV system, where again phi is a state transition matrix and ABCD or CBD are the parameter matrices of this LTV system. Okay, so along the same line of the continuous time domain, we can define these two subspaces, unobservable and unconstructible, on T0 to T1, consisting of all states x0 for which C phi x0 is equal to 0. Right? Because again I can take this entire part onto the left hand side and then denote it as y tilde. So I would have y tilde is equal to C phi x0. And if my C phi x0 becomes equal to 0, so for all those x0 for which we have C phi x0 is equal to 0 would comprise the unobservable subspace. Similarly, the unconstructible subspace on T0 to T1 consists of all states x1 for which this equation is satisfied. Now in the continuous time domain and the discrete time domain, we had seen a key difference in computing the state transition matrix, that in the continuous time domain we can compute the state transition matrix in both the directions. Okay, but in the discrete time domain we had seen some limitations, and this limitation arises because if you pay attention to this state transition matrix, which is phi t comma t1, where t is from t0 to t1, which means that I need to compute this state transition matrix backward in time. Say for this one, phi t comma t0, where t is t0 to t1 again, so the initial point is t0 and the final point is t, which is greater than t0. So I'm computing here state transition matrix forward in time, but here my initial point is t1 and t is from t0 to t1. So here I need to compute the state transition matrix backward in time, and this is only possible, that this matrix is well defined only when I compute x of t1, which is represented by this one, for all xt's, right? And this is only possible when all the matrices at different time from t0 to t1 minus 1 are non-singular. This is the same restriction what we had seen in the first week while computing the solution of the discrete time scenario. So when this does not happen, the unconstructibility subspace cannot be defined. Okay, but there is no limitations in the unobservable subspace. Okay. So talking about the systems, now given two times t1 t0, the system DLTV is observable whenever its unobservable subspace contains only the zero vector, and it's constructible whenever its unconstructible subspace contains only the zero vector. And the same definitions what we had used while understanding the concepts of the continuous time case. The Gramians would remain the same, it just the summation would appear instead of the integration, and also the time is in integer instead of the real number. So this is the Gramian, the observability Gramian, and this is the controllability Gramian, and the key results which characterizes these subspaces in terms of the Gramian is given by, it remains the same. Okay, also the derivation remains the same, so we won't go into the derivation of these result. Okay, now in the discrete time case, if I want to reconstruct, this is the formula you can use if your system is observable to reconstruct xt0. If your system is constructible, you can compute x of t1 using this formula, where we had seen a key use of the gramians, the respective gramians. Okay. Now the next concept in this observability is duality. So duality is a very important concept by which we will see a relationship between the results what we have derived during the controllability bit and also the test for the observability for the LTI system. So let's recall first of all the controllable systems for the LTI specifically. So given these A, B, C, D matrices, note that here that X is n dimensional, U is K, and Y is M. Okay, we will give some importance to that in the next slide. That so far we have seen that the CLTI is controllable if and only if the rank of the controllability Gramian is equal to n, where controllability Gramian is defined by this. Okay, now the CLTI is observable if the rank of the observability Gramian is this. So here we made use of the AB matrices, and here we made use of the AC matrices. Right? Now I will define a dual system in the sense that the X bar would be of n dimensional, but U bar would be the dimension of the output. So if you see previously, we have m number of outputs, but in my dual system I am representing it by U bar, m number of U bar, and k number of Y bar, and I represent my dual system as X bar dot, or by A transpose, C transpose, B transpose, and T transpose, where C transpose in this dual systems becomes my input matrix and B transpose here becomes my output matrix, and the state matrix and the input matrix and the output equation are taken as the transposes. Okay, now let's see the controllability and observability for this dual system. So for this representation, again I need the conditions would remain the same. It just I need to compute the controllability Gramian and the observability Gramian. Okay, so by taking A transpose and C transpose to compute the controllability Gramian, I would obtain this one. Okay, now for observability I need to see A transpose and B transpose, and using that pair I can write the observability Gramian in terms of the AB matrices. Okay, now try to see the relationship between this dual CLTI and the actual LTI system. So recall this controllability Gramian and the observability Gramian which we had seen in the last slide. So I put this thing on the same slide so that we can easily visualize the relationship between the controllability of the original system and the observability of the dual system. So this WC and WO are the Gramians of the original system, and this WC bar and WO bar are the Gramians of the dual system. Okay, so here WC, you see the pair AB matrix. So this WC and this WO bar basically is the same, right? Similarly, WO, that is the controllability Gramian of the original system, and the controllability Gramian of the dual system also remains the same. So based on this, we have the immediate result that the system CLTI is controllable if and only if the dual system is observable, right? Similarly, the CLTI is observable if and only if the dual system is controllable. So they both are equivalent. The result would remain the same for the reachability or the duality between the reachability and the constructability. So we can also summarize these two results in the form that the pair, if we only talk about the pair AB is controllable if and only if the pair A transpose B transpose is observable. Okay, and this is only valid for the LTI system. We will see that how these conditions varies uh, for the LTV system. So now moving forward to the observability test. So we had seen that there is a duality between the controllability and the observability. Meaning to say that whatever the results we had obtained for the controllability, they would be directly applicable to analyze the observability. So we will list out all the results of the observability without going into the proofs of those results. So consider the LTI system. So here we use the notations so that we can represent the discrete time and the continuous time with the same state equations. So from the duality theorems, we can conclude that a pair AC is observable if and only if the pair A transpose C transpose is controllable. Okay. Or because in the previous we had seen AB is controllable if and only if A transpose B transpose is observable. It's just the pair. So here we have replaced B by C and the results would remain the same. So this allows us to use all the previously discussed tests for controllability to determine whether or not the system is observable, particularly for the LTE system. So this we can visualize also. So on this pair A transpose C transpose, if I compute the controllability matrix, this would be given by this one of dimension kn cross n. Now I can define this matrix as the transpose of the observability matrix, where my observability matrix is given by this one. Okay, so the controllability matrix of the pair A transpose C transpose given by this, and whatever the matrix I have obtained after doing some simplification, I define the observability matrix as this one. That is to say, the controllability matrix is actually equivalent to the transpose of the observability matrix. Okay, so based on this equivalence, we know that if I compute the rank of the controllability matrix and it is a full rank, then the rank of the transpose of that observability matrix would also remain the same, and the rank does not change under any transpose. Okay, so we obtain the following results, that the following statements are equivalent. The system AC LTI is observable. Rank of the observability matrix is n, which is the dimension of the A matrix. So during the controllability week, we have defined this as the matrix test. The third is that no eigenvector of A is in the kernel of C. This is the eigenvector test. And the simplification of the eigenvector test, which we have defined as the PBH test, that the rank of this matrix is equal to n for all lambda belonging to the set of complex numbers. Okay. Now there was one additional result, that is the Lyapunov test for the observability, which assumes that the matrix A is a stability matrix. So we can say that the system is observable if and only if there is a unique positive definite solution W to this Lyapunov equation in the continuous time and this Lyapunov equation in the discrete time. And moreover, the unique solution to this equation is given by this. So we had seen the detailed results or detailed proof of these results during the controllability week. So the equivalence or the duality between the controllability and observability, particularly for the LTI systems, remains the same. Right? So the proof remains the same as what we had seen earlier. Now talking about the LTV systems, so the result we had seen earlier, so this is the same result what we had seen earlier, that this WO matrix should be non-singular, either for LTI system or for the LTV system. But in the controllability week, we had seen that for the time varying system, it is a bit difficult to compute this the observability Gramian. Why? Because it requires the computation of the state transition matrix. For the LTI system, the state transition matrix is basically exponential. But for time varying system, it is not necessary that it would be, or it requires detailed computation. Right? So, so this is if and only if. This is if and only if, because this is the necessary and sufficient condition for the observability. So if you recall that for analyzing the controllability of the LTV system, we take a different approach, and we had defined only the sufficient condition. Right? Similarly, we can define the in a similar way for the observability, that let A and C be n minus 1 times continuously differentiable. Then the n-dimensional pair AC is observable at T0 if there exists a finite T1 such that the rank of this matrix is equal to n. So now, instead of ensuring the non-singularity of this observability Gramian, we compute the matrix n, and then using those matrix n for 0 to n minus 1, we compute its rank. Okay, and this is how you can compute the n matrices. Okay, so this is only a sufficient condition, but not the necessary condition. So for time varying system, duality is more complicated, because the state transition matrix of the dual system must be the transpose of the state transition matrix of the original system, right? But this is not obtained by simply transposing the A matrix, right? So because of this reason, we cannot say that the controllability of the pair ATBT, or let's say the controllability of the pair ATBT is not equivalent to the observability of A transpose B transpose.